Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the equilibrium constant. Consider a mixture of ideal gases that exists in equilibrium at a specified temperature and pressure. Like entropy, the Gibbs function of an ideal gas depends on both the temperature and the pressure. The Gibbs function values are usually listed versus temperature and a fixed reference pressure P0, which is taken to be 1 atm. The variation of the Gibbs function of an ideal gas with pressure at a fixed temperature is determined by using the definition of the Gibbs function. From Gibbs equations, we have: for reaction of ideal gases at constant temperature, integrating, we get for an isothermal isobaric reaction, the Gibbs function change of the reaction is. For convenience, we define the standard state Gibbs function change as, or the Gibbs function change for the reaction is. For an equilibrium reaction, we have 0 Gibbs function change, and then, where Kp is the equilibrium constant, once the equilibrium constant is available, it can be used to determine the equilibrium composition of reacting ideal gas mixtures. Now, let's talk about some remarks concerning the Kp of ideal gas mixtures. Firstly, Kp of a reaction depends on temperature only. It's independent of the pressure of the equilibrium mixture and is not affected by the pressure of inert gases. This is because Kp depends on the standard state Gibbs function change, delta G0T, which depends on temperature only, and the delta G0T of inert gases is 0. Thus, at a specified temperature, the following 4 reactions have the same Kp value. Secondly, Kp of the reverse reaction is 1 over Kp. This is easily seen from the definition, equation 1385. For reverse reactions, the products and reactants switch places, and thus the terms in the numerator move to the denominator and vice versa. Consequently, the equilibrium constant of the reverse reaction becomes 1 over Kp. Thirdly, the larger the Kp, the more complete the reaction. If the equilibrium composition consists largely of product gases, the partial pressures of the products are considerably larger than the partial pressures of the reactants, which results in a knot value of Kp. In the limiting case of a complete reaction, Kp approaches infinity. Reactions with very small Kp values and a specified temperature can be neglected. A reaction with not Kp is usually assumed to proceed to completion, and a reaction with small Kp is assumed not to occur at all. Fourthly, the mixture pressure affects the equilibrium composition. This can be seen from equation 1391, which involves the term P delta N, where delta N is the difference between the number of moles of products and the number of moles of reactants in the stoichiometric reaction. At a specified temperature, the Kp value of the reaction remains constant. Therefore, the mole numbers of the reactants and the products must change to counteract any changes in the pressure term. The direction of the change depends on the sign of delta N. An increase in pressure at a specified temperature increases the number of moles of the reactants and decreases the number of moles of products. If delta N is positive, have the opposite effect if delta N is negative, and have low effect if delta N is 0. Fifthly, the presence of inert gases affects the equilibrium composition. This can be seen from Kp, which involves the term delta N, where N total includes inert gases. Sixthly, when the stoichiometric coefficients are doubled, the value of Kp is squared. For example, for this reaction, we have this equilibrium constant. For this reaction with doubled coefficients, we have this equilibrium constant, which is squared of the former one. Therefore, when one is using Kp values from a table, for example, table A20 in the appendix, for stoichiometric coefficients used in a reaction must be exactly the same ones appearing in the table, from which the Kp values are selected. Multiplying all the coefficients of a stoichiometric equation does not affect the mass balance, but it does affect the equilibrium constant calculations, since the stoichiometric coefficients appear as exponents of partial pressures in equation 1385. Seventhly, free electrons in the equilibrium composition can be treated as an ideal gas. At high temperature, gas molecules start to dissociate into unattached atoms, and at even higher temperatures, atoms start to lose electrons and ionize. The dissociation and ionization effects are more pronounced at lower temperatures. Ionization occurs to an appreciable extent only at very high temperatures, and the mixture of electrons, ions, and neutral atoms can be treated as an ideal gas. Therefore, the equilibrium composition of ionized gas mixtures can be determined from equation 1391. This treatment may not be adequate in the presence of strong electric fields. However, since the electrons may be at a different temperature than the ions in this case, easily, equilibrium calculations provide information on the equilibrium composition of a reaction, not on the reaction rate. Sometimes it may even take years to achieve the indicated equilibrium composition. For example, the equilibrium constant of the water formation reaction at 298 Kelvin is about 14th power to 10 from table A20 in the appendix, which suggests that a stoichiometric mixture of hydrogen and oxygen at room temperature should react to form water, and the reaction should go to completion. However, the rate of this reaction is so slow that it practically does not occur. But when the right catalyst is used, the reaction goes to completion rather quickly to the predicted value. Okay, that's all for this task. Thank you very much, and see you next time.